The first diagram on your left shows a semiconductor diode. The material can either be germanium or silicon. Let's assume it's silicon. That's by far the most popular semiconductor material being used right now. This would be N-type silicon. This is P-type silicon because of the way it's been doped. And if we connect this in a circuit, this is called a junction. Sometimes even called a junction diode. Here's a battery. Here's a resistor to limit any current flow. We find that current starts to flow in this direction. And we say that the diode is forward biased, it's on, it's conducting. If we go to the next diagram now, where it's the same NP junction, which will reverse the polarity in the battery, we find that now no current flows in this circuit, and the diode is said to be reverse biased, and it's off. So this is under normal conditions where a diode can be used simply as a switch to either turn something on or off, as the case might be. Now, silicon has the following characteristic, that when it is conducting, as it is in this diagram, that if you look at the voltage across the junction, it tends to be as much as 0.7 of a volt drop across the junction while it's conducting. We call that the forward voltage drop. Now, on the other hand, if we're using germanium, under the same conditions, we find that germanium tends to have a voltage drop of about 0.2 of a volt instead of 0.7 of a volt. And when we change the polarity and we have this type of situation, there's no current flowing, we call it a reverse voltage bias. So we reverse voltage, and we have present a situation which is really quite interesting because there's not a possibility here. If you make this voltage high enough in this reverse mode, you can cause the diode to break down and to start conducting again in the opposite direction this time than it would normally conduct. And that's called just simply the breakdown, and sometimes the phenomenon is referred to as a Zener breakdown. So if I were to make a sketch and I were to plot current flowing in the diode versus the voltage drop across the diode, we find that during normal operation, the curve looks something like this. As you increase the current flow, you tend to get a little bit more of a voltage drop, and then it seems to go down here to about 0, and then it just seems to disappear. There's no current flowing at all. And now you get the voltage out here negative enough across this diode, and suddenly it breaks down. But instead of conducting forward, it gives you a reverse current. So the current now starts to flow in a direction opposite to what it would normally flow if we had a forward bias. And this is called the breakdown voltage, VBR. And this voltage in here, which is about that 0.7 of a volt or 0.2 of a volt for germanium, is simply called the forward voltage, V sub F. And this is the characteristic you would find that's very common for most diodes. Well, in order to summarize all this into one simple circuit diagram, we do it this way. We say, let's imagine we had two parallel paths. One of them had a diode showing the direction in which current would normally flow through a resistance, and then we have a voltage at this point, and the parallel path consists of the reverse direction on the diode, then a resistor, and then we have a voltage with a reverse polarity from the one above. We have them connected over here like this, and this now becomes the equivalent circuit for the diode. Now let's explain what's happening here. If this is a diode current that's normally flowing, it would tend to go through here. This would represent the forward resistance, an equivalent resistance when we're in a forward mode. This is now ideal. There's no drop across this diode. It's merely here to give you direction, show you which direction the current is going to be flowing. This would represent the voltage across the diode, the forward. And so this path, at the upper path there, represents the equivalent circuit when we're dealing with the forward conduction. Now, when the reverse conduction occurs with the breakdown, what we have in that case is that this resistance is called R sub Z rather, which would be the Zener resistance. This would be the voltage, VBR, the breakdown voltage. And the two paths together, they could never both be operating at the same time. It's either forward normal operation or the extreme reverse breakdown. And in between, neither one should be working. So this is the semiconductor diode characteristics, the equivalent circuit, and we just simply symbolically show it this way. With the diode with a V sub D across here, and that's it. That's all there is to the diode. But this is just a circuit symbol. This is really an equivalent circuit, and this gives you an idea of physically what's happening.